washing and like lots of the
Saturated and chlorinated. No, those like recycled shoes. But they have different colors in that.
That looks like what's with method fuels.
Yes. Yeah, I mean, it's also like.
Yeah.
Number 2. What'd you get for number 2?
Yeah.
Yes.
By the way, I might need to leave like around 3:45. I've got some things to do in the evening, and I have an early flight tomorrow.
Sure, not a problem. Thanks for telling me.
I still live at home, so my fiance is the one who lives there. So thank you. I'm getting married in December. So the week before finals. That's not how I found my there's a shorter certified faster.
Oh yeah,
I don't know what that is. Not from Ohio.
It's a science museum.
All right. So let's go ahead and start talking about this. So given this picture, can you, hopefully without too much trouble, describe 3 practical barriers to recycling of waste plastic streams? Yes.
Well, for one thing, just in that picture, there's probably like 20 or 30 different kinds of plastic alone.
I don't know about 20 or 30, but yeah, there's several for sure. Yeah, so that's one aspect of it. What does that mean, though?
Yeah, they're like labels, caps, basically.
Well, it's one at a time here. So the first option, how do we overcome that first barrier?
Right. There's several ways, but first of all, the one that's often used now is just like weight sintering, basically trying to separate the plastics out by different molecular weights.
Who does that?
At the plants, recycling plants.
They separate by molecular weight? That would be a hell of an achievement.
Not by molecular weight. They try to like use weight to separate out the different types of materials.
Oh, you talk about density separation.
Density
then. Yeah. What's cheaper than that, though?
Just stop making things out of weird kinds of.
Well, now you're thinking practically. I'm saying what's done now. So I go to the Rumpke facility.
Different recycling bins.
Well, that's not what's done in Columbus. That's done in California. They don't do it here. So at Rumpke, they have people who are paid to stand there and say, this is 2, this is 1, this is something else. All right, there's the manual side. What was the next comment?
I was going to say density, but I can add another idea. You have like bacteria in your potentially recyclable material.
Yeah. Okay. And so what's that means the direct primary recycling is a problem. How do we overcome that?
I think it's just processed at higher temperatures to like burn off and like act as like a sanitizer.
Well, as we discussed last time, it's amazing that this is an issue since it's going to 250 degrees centigrade. You think that'd kill off everything, but the FDA still doesn't like it. So you can't take a PET bottle and directly reform it into a PET bottle. If you depolymerize it, then you can form a PET bottle. But I can't take the milk jug, one of which is in that picture, and directly recycle it into a primary milk jug. FDA won't allow that. So what we do is we do a secondary recycling. We make something less demanding that we're not going to try to eat off of, like at least not normally, like carpets and clothes and insulation and things like that. Yes?
I couldn't hear over the.
Oh, I'm sorry. Yeah, so which part did you not hear? The first one or the second one?
Basically, the first part come on. I just kind of heard.
Couldn't hear
parts of the
anything you guys were saying all over.
Yeah.
The whole conversation.
Okay, the whole conversation. So the first one is we have to sort these things, and we can use density separation, as Kevin pointed out, and that involves chipping all the plastics and then separating the chips from each other by density. A little more practical than that, at least on the front end, is to hire people who will say this is one, this is two, and this is something else, which is basically the only separation that is really of importance when it comes to actually recycling plastics. All right, so they do it kind of what we do, except they have a much better eye. So, you guys, I can look at this and I can tell you which ones are 1 and 2. You might not be there yet, but it doesn't take much of an eye to separate things based on how they look. And polypropylene looks different, PVC looks different, polystyrene looks different, and they're all visually different. And by the time you worked for Rumpke for a little while, you can pick it out at 10 yards probably. Okay, so that's kind of the answer to number 1. Number 2, which was, what was the other concept we talked about?
Like bacteria.
The bacteria, yeah. So the barrier, it's kind of a barrier. We want to recycle plastic, and it'd be great to just recycle it right back into what it was. But the problem is it's been out in the real world where viruses and bacteria exist. So the FDA says you cannot recycle this gallon milk jug right back into a gallon milk jug. You can make a park bench out of it, but we're not going to let people eat off of that thing, even though it has to go through these incredibly high temperatures during the melting and extrusion process. So that is kind of a barrier to direct recycling. Does that cover it? Yes?
Didn't we also say that like colorants in them, you wouldn't necessarily want to do with them?
Yeah, that's exactly right. So one of the great features of plastics is that they can be colored to be whatever we want them to be. So whatever that is some kind of red thing, all right? And we may not want our bottles, or if we wanted to make a bottle out of this, or our fibers, if we want to make fibers out of it, we might not want them to be red. So Rumpke may say, hey, throw that piece away, even though it's number 1 or number 2, because it's red. All right, and our downstream recyclers don't want to deal with that. And so that's another barrier, and you overcome it by manual labor. Yes?
What was the solution to the removal of non-plastic materials? What was the solution to, like, such as having viruses or bacteria on them?
Yeah, the solution is to, A, not use primary recycling. All right, so you can't go from bottles to bottles. You can go from bottles to carpet, or bottles to clothing, or bottles to insulation, or bottles to fuels, or bottles to the incinerator. There's a whole bunch of options beyond the primary one.
Is the cost of recycling versus the money you get back for sewing material a practical barrier?
No, it's typically still amazingly cheaper to work with virgin plastics than it is to work with recycled plastics. So that's why we as consumers, if you live in Franklin County, you're paying Rumpke a recycling fee. All right, that makes them whole as far as their costs are concerned. All right, so it's subsidized at this point in history, unfortunately. All right, this stuff is free. It's a waste stream that has no cost to it, but still, given all the things that have to happen to all this stuff in order to make a product out of it, it's not profitable. Yes?
I just had another barrier.
Yeah, what's that?
Food contamination?
That's a similar thing, yeah. So, but how do we address that? That's not as big a...
Like on OSU's campus, if there's food contamination, they just throw out the whole like recycling bin, basically.
The whole recycling bin?
Not the bin, like all of the contents in it. So my fix was education, teaching people what to do.
Well, you can do that, or else if you think about that video, the Chinese video, you shred it into plastic, and then you just clean off all the fluid in a chemical
They
bath.
can't even get there if they throw it all out.
Well, yeah, I'm not sure. I know pizza boxes are like that. You can't recycle a pizza box if it has pizza guts on it.
Yeah.
But this is plastic that can't be recycled?
Yeah, or like, if there's even one piece of contaminant in the OSU recycling bins, they just throw it right out because they can't deal with it.
So how do they determine that? If there's a slice of pizza in with all the other plastic bottles, they throw the whole thing out?
Yeah, basically they just throw out all the recycling on campus. They don't
Well, that's one solution to the problem, I guess, is just throw it all away. Yeah. All right. Yeah, I wasn't aware of that. That seems pretty extreme. Any other questions? Yeah.
Do we have enough land area to recycle? Enough land area?
Enough land?
Land areas.
Land area?
Uh-huh.
Are you talking about landfills?
Uh-huh.
Oh, yeah. Yeah, I would say that's not a recycling option. That's just throw it in the ground option. I wouldn't call that recycling. Unless you have a time scale of like 100,000 years, it's not really recycling. But that's what happens if you can't recycle. Any other barriers? All right, so number 2, which I get the sense that many just kind of didn't try it. Once a particular plastic is isolated, so we go to the trouble of hiring people to do this, and hopefully they do their job, and all the number 1s go in one bin, and the number 2s go in another bin, and then they go off to get shredded. What are the barriers to successful secondary recycling, which was what we just talked about, making something that is not as demanding out of an object? Yes?
Water.
Water? What does that mean?
So water gets inside, especially with PET, it gets inside and cuts the chain ends off and causes it to have higher melting and glass transition temperature in the recycled plastic than the
Yeah, that can happen. But so we call that chemical process. Scission is the effect, all right. But the hydro part of it is hydrolysis. Okay. All right. So water attacks PET. It doesn't attack polypropylene, by the way. So PET suffers from this, but other plastics don't necessarily suffer from this. So that is a huge barrier. And following along that, what are the potential effects on molecular weight? Yeah, it goes down. We decrease the molecular weight. And it's a question of how far can it go? How low can you go and still have a viable commercial product at the end of the day? All right, so we know it happens. We can do things to avoid it upstream from that, but we know it happens. And these are important because why? Why is molecular weight significant?
It affects properties.
It affects properties. Mechanical properties are the one we're all used to. All right, but there are other potential chemical effects, especially if crystallization is higher than it used to be. All right, if there's more crystals, they're more perfect, the diffusion barrier will increase. But we like to think about mechanical properties first. We know it can become more brittle. We also know that, aside from molecular weight, when these chemical reactions occur, we're putting more OH groups into the PET. And if this occurs enough, then it becomes more brittle because of enhanced secondary bonding, right? So you have something that is adding to the ability of the plastic to hydrogen bond, which, makes it stronger, but it also makes it more brittle. It's always a trade-off, always a yin and a yang. Yes?
How does the recycling plant know that maybe you give them a bottle that's been recycled many times and it's no longer desirable to recycle that again? Like, how do they know, to not recycle it or to choose to throw it away versus recycle it?
Yeah, that's a good question. So in the absence of being able to measure molecular weight on the fly, which would be awesome, we don't really know that yet. We don't have a way of saying this bottle or this fiber has been recycled one too many times, and so we don't want to use it anymore. Right now, we don't have a good way of doing that. But what we do, and this is kind of a consequence of this primary to secondary, is we start with a primary material and recycle it into, like I said, insulation, carpet, things that aren't as demanding, and those things aren't likely to come back to the recycling plant. All right, so they don't recycle carpet as far as I know. I've never seen that done. That usually gets landfilled. Yes?
So, is there a way to possibly do the secondary processing on the plastics in a controlled environment that would allow water to not get into the system?
Yeah, well, so that kind of goes back to that video. So there's a step in the video there where they take all the plastic chips and they put it into a rotating can that's at whatever it is, 110 degrees. And you see this steam coming out of the can, and they're drying it. So they're trying to get rid of that water by drying this stuff ahead of time before they turn around and make it into fiber, as you saw in that video. And that drying step is for that reason. They're trying to get rid of the water so that the clothing or the carpet, whatever it is they end up making out of it, isn't too weak. I mean, fiber, it's, you know, clothes aren't exactly a demanding mechanical application of plastics, but they need to have a certain level of strength. All right, and so if you make clothes that fall apart, that's bad. Any other comments? Can you hear me over there? Okay. All right, and the last question, do you believe that plastic recycling efforts are ultimately going to be successful? Yes?
I think to an extent it can be. I think there will always be waste. It's just about how much waste we can reduce. And I think there's always going to be plastic that can't be recycled.
There are always going to be plastics that cannot be recycled. There's a lot of, yeah, so I looked up that thing about the Coke bottles where they say, keep the cap on this bottle. And I looked it up, and as far as I can tell, it's just PR. It doesn't really mean anything. They're saying, oh, keep the cap on the bottle so we can turn it into plastic pails, which is, there's not a hell of a big market for recycling with plastic pails. Anyway, so there are things we can do with recycling numbers 3, 4, 5, and 6, but in reality, as far as we know, there's not going to be a big market for that. But with 1 and 2, we can keep doing that with 1 and 2, and if things become really efficient, then the problem becomes what I mentioned earlier, these molecular weight issues. All right, and so if we get really good at turning plastic around in the waste stream and recycling it, if tomorrow they said, thou shalt not make 3, 4, 5, and 6 anymore, which I'd be all in favor of, except for PVC, kind of hard to replace that. Then we'd have a lot of plastic in the waste stream that we could recycle, but at that point, and we're not there yet, this issue of molecular weight would probably rear its ugly head and become more of a problem, because if it's recycled once, molecular weight drops, recycled again, drops further, and so forth and so on. And so eventually there's going to be an issue associated with those properties. Any questions about that? Yes?
Can we just make, since Paraffin already, sorting out all the plastics, wouldn't they be able to burn the stuff that isn't easily recyclable if they still have the power plant going?
Yeah, they can burn stuff, sure. Yeah, that's one way around it. Now, of course, you want to burn PVC unless you have a higher temperature.
PVC, but
yeah.
already sorting it out.
Yeah, you could sort it out. You could always burn everything. It's a question of, does it make sense? Yeah.
So then we get into an issue of CO2 getting in the atmosphere.
Yeah.
Do we have enough? Is there a way to limit that at all?
Yeah, well, that's the problem. Is that CO2 gets in the atmosphere, the ice caps melt, and Atlantic City goes underwater. Things like that happen. Bad stuff happens with that option, and we don't have a good way of scrubbing CO2 out of the atmosphere right now. So all we can do is try to prevent it from being generated in the first place. That's not why plastics recycling began, but it's a good reason to keep it going. Any other comments? All right, please put your names on there, on those sheets if they're not already on there, and pass them forward. To find a paper cutter and take care of this problem. All that paper make you write more than you would normally? Thank you. Is that it? All right. Okay, so today we start on the second half of the class, and this is going to be a little more chemistry oriented, not a lot. Okay, it's a far cry from organic chemistry, believe me. And so we'll talk a little bit about how polymerization of polymers happens, and we'll talk about polymers that we haven't talked about previously. So that's going to be new and different as well. So there's a little bit of review here, most of which you guys should already know, but I'll try to hit the high points because it might be helpful to you in the context of the exam. So we know what a polymer is. It means many mers. So polymer is where that name comes from. Scientists prefer the name macromolecule, those scientists typically being chemists who like to think of everything in a molecular form. But I find myself using that phrase because it really helps describe the fact that we have a chain. And it's a little more precise than saying we have chains. These are formed by combining large numbers of low molar mass molecules, and so we have this monomer, and a key part of this that we'll talk about more is the fact that that monomer has active N groups. All right, those are, we call them functional N groups. They can react with other N groups of the same monomer, or they can react with N groups of an entirely different monomer, or 3 other monomers, or they can cross-link in 3 dimensions using those N groups. So it all depends on what you want as far as the resulting goal of this is concerned. And so we'll spend more time talking about that today. But ultimately, these things are combined into a polymer chain, which, at least in this illustration, we've got the 2 ends here. And this would be considered an oligomer, by the way, this particular cartoon. This is not a polymer yet. It hasn't gotten there. It's nowhere near long enough to be considered a polymer, but it gets the point across. We design these structures so that they have certain goals once they get to a specific molecular weight. And this process happens in a manner that I've shown you previously. We have ethylene gas, and in this context, these double bonds are the active species at high temperatures and pressures, and especially in the presence of a catalyst. All right, we absolutely have to have catalysts in these systems. Otherwise, this process would be more troublesome. We get polyethylene out of that ethylene gas. And we know that molar mass or molecular weight is very important. Typically, more than 10 kilograms per mole for reasonable properties that are associated with a plastic. So again, it has to be a certain length to be useful. And this shows you stuff I've given you before: gases, liquids, high viscosity liquids, and finally get to solids, and then useful solids at greater than 10,000 typically. And so we know that this dominates properties. So if it's just polyethylene, we can use it for cooking, or we can use it for gasoline. And so this is where octane comes from. It's 8 chains, 8 monomer long polymer. Kerosene. Has anyone ever seen kerosene? All right. So one person has seen kerosene in their life. Okay.
You mean chemical structure or like?
No, I mean the actual stuff.
Oh yeah.
Okay. Oh, you've seen kerosene. All right. Yes. Okay. All right. So some campers or hunters here, I assume. That's usually where you see kerosene these days. So it's something that used to be around a lot. Kerosene used to be a very popular fuel. It's hardly ever used anymore. And then above that, we get to oil and greases. And paraffin wax, we'll talk about that in a minute. That's not candle wax. It's a different structure. And then we can get to things that finally have the proper molecular weight to be considered a useful solid, such as for bottles. Polymer applications. If we disregard metals and inorganics, we observe that practically everything else in the world is polymeric, which is sort of simplifying things a little bit. But in this context, we think about biological structures as being representations of polymers, which they sort of are. And so that is not too far off. So if you think of wood, you think of everything growing as being polymeric, there's an argument to be made that that's the case. Some of the many applications, we have packaging, clothing, structural materials, adhesives. Remember I talked about adhesives last time. When we use them as glue, they can be a problem in recycling because they're not PET, they're something else. We need to get rid of them. And as you saw in that video, they treat it with a caustic bath that dissolves that glue and rinses it away. And so adhesives is one of those things that we kind of take it for granted, but as 3M demonstrated, you can take a tiny bit of a special adhesive and put it on polyethylene terephthalate tape, and you generate $1 billion industry for something as trivial as an adhesive. So that's certainly very important. And of course, paints also have polymeric components to them that help them have the right viscosity and a lifetime that's desirable. And we also use these in some electronic. We talked about some conducting applications. We also briefly mentioned electroluminescence, which is OLEDs, which is all our screens these days are made from OLEDs. So those polymers are very important there. And just as a more simple example than that, circuit boards are made of epoxy resins. Okay, and so this is not a thermoplastic, but a thermostat. And this is a wonderful technology now. I found this out a couple years ago. You can dream up a circuit overnight, submit it to a website, and then the day after that, they ship you a circuit board with that. Direct from, I think it's China where they do this. They have machines that take your design and just make the circuit board without humans involved, and they'll ship it to you right away. So
That's pretty cool, actually.
it's very cool. Yeah, we didn't used to have that, so very nice. And then medicine is a very important use of polymers, and so the only thing that we used to have to make syringes was glass. All right. Nowadays, though, we have a much broader array of plastics that are used. These vacutainer things that I guess are used to sample everyone's blood now, as far as I know. Those didn't used to exist. You couldn't make them out of glass. You can make them out of plastic, and so this just spawned this entire new application in which everything you see there, except for the paper labels, if there are any, is a plastic of one form or another. Polyethylene, polypropylene, from the looks of it, for the most part.
And the needles, probably.
The needles, the Yauchi part, yeah, that's not plastic, yeah. Okay, and so we're replacing materials such as wood, aluminum, steel, and glass, although not metal needles yet, maybe someday. Oh, did anyone see that article about phthalates? There's a thing in Google News about phthalates. All right, phthalates in plastic and how bad they are for you, and this issue of children getting mutations and things like that in various diseases, which may or may not be true, but they talked about PVC as being an example. And that DEHP, the 2-diethyl hexyl phthalate, that's an example of one of those phthalates. It's not in small quantities, it's in huge quantities in some plastics. And so if phthalates are a problem, then we're all in trouble. All right, so classification. We have synthetic organic polymers, and then we sort of think of that as mostly what we care about. So polyethylene is organic, polypropylene is organic, and they all have the same commonality of the carbon-carbon chain sitting there in the backbone. And coming off of that, we have whatever side groups we're thinking of, which can be chlorine, and the rest can be hydrogen, of course. And then what we do is, as you've already seen, we can treat this algebraically and swap these things out. And we get an entirely different polymer based on the identity of those side groups. All right, so from this, the entire plastics industry has been built. We do have inorganic polymers, and these do not have any carbon in the backbone. And the example that I've shown you before is this silicon oxygen silicon, whoops. And here we use CH3 as a side group. So like polypropylene, except it has an inorganic backbone. And this is known as polydimethyl siloxane, more commonly known as PDMS, MS, which is more commonly known as silicon rubber. Silicone rubber. Don't call it silicon rubber, people will laugh at you, all right? Although it's how it's pronounced. Anyway, so there's no carbon in the backbone, silicon rubber. There are other examples, but they're pretty obscure. Polyphosphazines. This is one. Whoops, you didn't see that. All right. This is the polyphosphazine, which has phosphorus and nitrogen in its chain. I don't think any consumer is ever going to see these. These have been used in some medical and research applications, but other things do exist. But the SiOSI is by far and away the most important inorganic polymer that's out there. And it's not just CH3, by the way. You can have a variety of things there besides CH3 and still make a rubber out of it. All right, there's entire catalogs stuffed full of examples of these types of monomers. And then we have natural polymers, proteins, polysaccharides, cellulose, natural rubber. All these things are also natural polymers. We don't normally think of proteins as being polymers, but if you take all the conformation away from a protein, you have a polymer. The distinction is the shape and how the side groups are presented. That's what makes it an active protein. Take all that away, and it's just a polymer. So it's accurate to call it at least a low molecular weight polymer. Okay, by processability, we have thermoplastics, and as you guys should be familiar, thermoplastics and thermostats are very different from each other. Formed with heat and pressure, recyclable, at least more or less. Yeah, sometimes recyclable is sort of like a talking point rather than a reality. We know we have crystalline and amorphous forms of these, and that their properties are very different, and we can mix them up, and we often do. Especially, we'll talk a little bit more about biomedical polymers in this half of the class, and in that context, it's very important to be able to play around with the percent of crystallinity, because if we have a polymer that's been approved by the FDA, and I see this all the time, people say, oh, we made this polymer over here, it could be useful in this application. Well, first you've got $10 to $100 million of barriers to get through before that polymer becomes anywhere near as useful as PLGA or PGA or PLA, which are already out there. The FDA has approved them. And so what that restriction means is they really try to engineer what we have. PLGA is a great example. You can change the crystallinity in PLGA, and it goes from being a suture to being something else if we change the amount of crystallinity. Same chemical composition, we just change the crystallinity. It's very tightly regulated and can give us very different properties. Polyethylene, polystyrene. Thermostats, they can be formed with heat and pressure at least once, but once they've been formed, that's it. We can't recycle them, all right, because it's a three-dimensional network, and so we don't know how to do anything else than just burn those. Yeah, I was in the hardware store. They have these crack injectors for masonry. It's made from two-part epoxy. It's a giant tube of two-part epoxy that mixes as it goes through the nozzle, and then you inject it into the crack, which is pretty neat. But you can't recycle it, all right? And resins, of course, you see those in the grocery store. Okay, so this area is very interdisciplinary, and the best example that I can give of that is the fact that we don't have a book in this class. And I tried for many years to find a book for this class. And there are two kinds of books in polymers. Ones that are written by chemists, and the other ones are written by chemical engineers. And that seems to be pretty much it. I used to use a book by Eric Grulke on polymer processing. I taught from that for a few years. And that was okay, but it was still a chemical engineer's book. And the problem is that chemical engineers see polymers as this rheologically boring gray fluid. All right. They don't want to know about crystallinity. They want to know, how do I move this fluid from location A to location B in my plant? And how do I injection mold it? And they have all kinds of software that can tell them what to expect, but they're not going to talk about crystallinity because that's not what they worry about. Polymer synthesis, on the other hand, so if we go across the street, the chemists say, oh, I've made a milligram of polymer. That's a lot, right? And so that doesn't really jive very well with what materials people care about, because we want to make a ton of polymer, not just a milligram. All right, so there's very different perspectives on polymers. Synthesis, like I said, is chemistry and chemical engineering, characterization. And when I talk about characterization, I'm talking about solids characterization. That can be MSE with some physics thrown in. So that's part of what you're getting in this class, is the physics view of polymers. Physical properties is, again, primarily MSE and physics. And then processing is mostly chemical engineering and a little bit of MSE, all right, where we do try to correlate properties with what it is we're making and what we've done to make it that way. And so it's a very interdisciplinary field with a history that is rooted in chemistry, but has since translated all the way up to large-scale production that you see from chemical engineering. And so there are, as it says, molecular design aspects of polymer properties. And so we know that we can design a polymer to do certain things based on the architecture, as we call it, what we stick into the side groups and how we arrange them in space. That's all the architecture, and that gives us these different properties. And then polymer physics deals with structure and properties. That is a very deep area of us as well. All right, so first example, polystyrene is rigid, natural rubber is soft and flexible. Okay, so polystyrene, and again, this is normal polystyrene, not HIPS polystyrene, versus natural rubber. Why is there a difference? They're both polymers. What makes them have these very different stress strain curves? And this can be 10%, and this can be 1300% easily. Very different net extensions. Yes?
Composition.
In what way? How does composition affect this?
Chain formation.
Which one is it? Chain formation or composition? I mean,
I'm saying like composition affects chain formation.
yeah, but I thought we were going to go in the direction of the side groups. All right. So how might the side groups between these two different materials affect their properties? Yes?
What's the side group for natural rubber?
All right, so rubber, that's a good question. Rubber is primarily, you'll see some examples of that actually following. This is more like CH3 side groups, typically stuff in the middle. All right, typically no oxygen, although that's not always the case. Yes?
Does this have to do with rubber toughening, like with second phase particles?
Well, that's a consequence of these properties. So we have these very soft materials, which is what we think of rubber as being very soft, and we use that to toughen things. But by itself, it's soft because it doesn't really have any secondary bonding to speak of. It's just CH3. All right, and so we don't have strong interactions. Now, it turns out we also don't have that strong secondary bonding in polystyrene, but what we do have are large side groups. So we have those phenyl groups. A few years ago, they did a study where they listened to polystyrene. This is definitely a physics experiment, and they could hear as they strained it. They could hear the phenyl rings popping out of the matrix. All right, it was so difficult to do that it makes noise at a very small scale. All right, because these big groups have to slide past one another, and so that's something that is a part of polystyrene, which makes it have some of these properties because it's difficult. Whereas natural rubber, on the other hand, can continue to strain because those side groups can slide past each other very easily. They're just CH3s. Okay, why does it go so far? What's the other thing about rubber that we haven't talked about? Yeah?
Cross-linking.
Cross-linking. All right, so when we make rubber, it ain't rubber until there's been some cross-linking done. Okay? Whether it's from rubber trees in South America or a chemical plant in Akron, we have some cross-linking that's going on. And so that allows for all the slippage, but it doesn't let things separate because it's got cross-linking that holds the chains together as it keeps pulling and pulling and pulling on all those cross-links. Let it go, and if it's a rubber band, it'll snap back to the same dimensions it had originally. Okay. And so again, that's not present in polystyrene. Polystyrene has some snapback and nothing like that, though. Any questions about that? Hopefully that all makes sense at this point. All right, we also have very different TGs for these systems. For polystyrene, it's 100 C. For natural rubber, it's less than 0 C. All right, and this is one of the consequences we like to see for polystyrene if we didn't rubber toughen it, okay, and we want to use it in a structural application. It can actually work relatively well as long as we don't bump it while it's being loaded, all right? It's a very brittle material, but it's got a pretty high modulus, so it can withstand some direct compressive loading, much better than HIPs can. All right, but and that's one of the reasons why is that its glass transition temperature is above us. All right, rubber's is below us by a considerable amount, which is one of the reasons why rubber is soft and pliable and stretchy. All right, because it's well above its glass transition. And this just gives you some idea of why that's important. So we know. Go ahead. It's okay.
You gotta wait till I'm crashing.
Sure. We have glassy materials, and we don't mean glassy as in silica. We mean glassy in terms of properties. It's like a glass. We go through the glass transition, and we get what's called the rubbery plateau. And some people, old language is leathery, showing you what people were thinking of when this stuff first came out. And that's kind of where we use these things. And typically, we like room temperature to be slightly above the glass transition. All right, so we get the best of both worlds. Some of the strength, but also the toughness. And then as we move to even higher temperatures above that, over here we end up with a melt. Okay, and I'd also like to point out this is log of modulus. So you know that's compressing a lot of things in a small space. So keep that in mind when you look at these curves. Any questions about all that? All right, So getting back to some things I talked about at the beginning here, we have paraffin, which is made of polyethylene. As you saw, it's a relatively low molecular weight polyethylene. Polyethylene sheet is also made of polyethylene, and here I'm talking about stuff like Saran wrap, which is what you're familiar with, but they have different mechanical properties. The same chemistry is working. Small molecules typically can be a liquid. Paraffin, let's see, some of you guys have worked in the lab. Have you dealt with the paraffin film? Anybody? Okay. Paraffin wax or film?
Wax.
What do you use the wax for? For
Crafting.
crafting?
Whenever you're grafting branches onto trees, you cover it.
Oh yeah. Okay. Yeah, there's that application. Yeah.
I don't remember if it's wax or film, but there was like a sheet of paraffin that you can like use to seal things.
Yeah, exactly, right. And it's really useful in that context because you can seal it around the top of a beaker and get a reasonable seal. You can deform it because it's soft, and so that also helps when you're trying to seal things together, and so it also helps that we can mold it around a tree branch if we need to. And so it does have utility, but it's very different in terms of what it compares to where the polyethylene sheet, which can be easily over 10,000 molecular weight, and also I should point out orientation. As you saw when I passed that grocery bag around, we make use of both what the molecular weight advantages and the fact that if we align it along the strong direction of the carbon-carbon bonds, we'll have a stronger film as well. All right, but this is all a function of the molecular weight giving us higher mechanical properties in that context. Any questions about that? Should all make sense. Okay, so commercial polystyrene is transparent. Whoops. Polyethylene sheet is not transparent. Why? Crystallinity. We think about the 1 gallon milk jug. We know it's not transparent because it's got a little bit of crystallinity in it. Polystyrene is typically now made in atactic form, so it cannot crystallize. All right, and that's why we use polystyrene in things like multi-well plates or things that you need to see through, because it's amorphous, it's easy to see through, it's got no crystalline borders to refract light. They have different amounts of crystallinity due to differences in structure. We can't make atactic polyethylene. That should make sense, all right, at this point. And that polystyrene, we have a large phenyl group, and this issue of controlled tacticity in the structure means that we're not going to get crystallization, and so it prevents the formation of crystalline structure if it's controlled correctly. But as polyethylene, it's really hard to avoid because of the fact that we don't have tacticity working for us. And so polymers can be different from each other because of intermolecular interactions, secondary bonding, chain-chain overlap entanglement. All right, we've introduced that concept when we talk about crazing. It's very important in crazing. Again, if we didn't have entanglement, we wouldn't have crazes. It would just be a dumb liquid, and it'd slide past each other, and it would never craze. Molecular weight, crystallinity, and then of course cross-linking, as is crudely shown here, will give us very different properties of different polymers. Okay, so we have some new stuff here. So there are some organic chemistry concepts, but not many. All right, very few. Has anyone had an organic chemistry class? Okay, it's murder. All right, so it's way harder than what we're talking about here. Okay, so yeah, like the alpha beta substitutions, they do that in that class and all that fun stuff. It's just, yeah. Anyway, I took three quarters of it. So anyway, I actually like organic chemistry, but most people don't. Single bond, single pair of electrons. So we have carbon-carbon, carbon-hydrogen. Double bonds, we have 2 carbons with a double bond, which gives us very different mechanical properties. We have monomers, which is where the name polyvinyl chloride comes from, by the way. The monomer is called vinyl chloride. And we can have a variety of different ways of making up a chain. This could be considered a copolymer, for example, depending on how you do this. And then we have this pattern aspect of polymers that's important. But then getting into things that we're talking more about, we have different polar groups. We have esters in this context. And you guys have kind of seen this already. And you'll see this again, so you don't need to worry about it too much today. That's an ester. And then the amide, I'll give myself a ton of room. The amide is alright, that's an amide, and we use these to build polymers. And then we have the urethane, which is carbon, oxygen, nitrogen, hydrogen, and this can sometimes be R, meaning that it doesn't terminate in hydrogen, it continues on in another polymer chain. And then the last one is carbonate. Yeah, so carbonate is another structure. Again, you'll see this later. Actually, you'll see more of it this lecture. And so we have these different structures, which, as you'll see, give us building blocks. We also have a variety of polar groups, and that includes some things we just talked about. Remember that these have oxygen, and they also have nitrogen, both of which can engage in hydrogen bonding. And then we have nonpolar groups which don't. They only engage in just things like dispersion bonding. Okay, again, you'll see this in great detail again, but you're going to see more of it. Any questions about that so far? And so this is an interesting chart that shows covalent bonds. The energy is very high. We know that. That's how covalent bonds run. We know that the bond length is 0.154 nanometers. We know that the bond length of carbon-hydrogen is also very small. It's because hydrogen is very tiny. You can get really close to that carbon atom when it's pulled in. And then we can also have a different bond length when we have carbon and oxygen together. Maybe more interesting, though, is the fact that van der Waals bonds are about 0.4 nanometers. All right, so those are typically how close the polymer chains will get to each other when we talk about just dispersion bonding or dipole bonding. All right, the energies are much, much lower than we see for covalent bonds. When we go to hydrogen bonds, however, the energy goes way up. So we have oxygen bonding the hydrogen bonding to another polymer, for example, and there the bond length also drops, so they can pull polymers closer together. And this is another reason why PVC is so much stronger than polyethylene, because the chains are a lot closer together. It's harder for them to slide past each other, along with everything else that's at work. And of course, every polymer has van der Waals. And you guys have seen this dipole-dipole interactions and how these form. This is just showing it in the context of a different polymer formed by something called a nitrile group, in which we have a triple bond between carbon and nitrogen. So triple bonds can also form. We talked about this when we talked about acetylene gas, which is a bunch of triple bonded carbons. All right, and in that context, we have partial positive charges and partial negative charges, which can then be attracted to partial positive charges and partial negative charges on other polymer chains, or on the same polymer chain. You just have to get close to each other, and you have this type of interaction. All right, and that is in the category of hydrogen bonding. This is also something that can make some sense. In that we have partial positive, partial negative, and these guys can interact with each other. Now, realistically, of course, this is head-to-head bonding, not likely to actually form, and so that is one possibility. But the reality of it is, you're much more likely to get hydrogen bonding in these systems, and that does involve a hydrogen interacting with these dipoles. That's a whole lot easier than what we're showing you here, but it is still possible for this to happen with these structures. All right, and this hydrogen bonding is particularly strong in polyamides and polyurethanes, phrases that you're going to see later on. Hydrogen bonds include chlorine, fluorine, oxygen, nitrogen, all interacting with hydrogen. All right, so they're very strongly electronegative. They find a really positive hydrogen, a tiny little hydrogen. They get really close to it and attract it very strongly, and that's a pretty good bond. That's a hydrogen bond. It's a secondary bond. It can be broken and then reformed. That's one thing at looking at these concept tests from the last time, which I was just grading. When you say secondary bonds break, be sure to mention that they reform. Okay, they don't just break and dangle there uselessly. They find something else to secondary bond to, right, instantly. All right, so keep that in mind when you talk about secondary bonds. And this is just showing you the structure of this polyurethane. And if you recall, I talked about polyurethanes before. We have the soft segments. These guys are all soft. come on, not sift, soft, all right? And then we have what are called the hard segments. And you can kind of see why. We get hydrogen bonding between the hard segments because they can. When they hydrogen bond, it holds those chains together and gives you strong bonds. And if it was made entirely of hard bonds, or hard groups, then this would be an extremely brittle solid. But what we do in this concept of a copolymer is we mix it up with the soft stuff, and by changing the length of this soft chain, we can change the overall properties of the polyurethane. All right, so it's tailoring, it's mix and match, however you want to describe it, it's very useful. There are dozens, if not more, polyurethanes that have been planted in humans, and this is because you can tailor these properties so much for desired properties in vivo. Any questions about that? Very handy approach. And so this is just showing you some structures of commonly used polymers, most of which you've seen before. So not too much to talk about here, except for this one here at the bottom, polymethyl methacrylate. You guys have not seen this previously, and so you'll become familiar with this as time goes by, and you can see it's got this odd side group that makes it polymethyl methacrylate. The only other thing to talk about is the fact that there's a spelling error here. It's not fluoroethylene, it's tetrafluoroethylene, okay? So don't make that mistake, although, well, we don't have that one on test yet, but it is a common spelling mistake. And then other side groups that we'll be concerned about: polyacrylamide, polyacrylic acid, polyvinyl acetate. You know, all these things should at some point become familiar to you. And then, as was mentioned a little while ago, we talked about rubbers. And so now you're seeing the actual chemical structure of these rubbers. There's no oxygen in these particular rubbers. It's just CH2 and CH. All right, so weak bonding. These guys can slide past each other. All right. You have polybutadiene, which is used in tires, polyisoprene, which is used in things other than tires. These are both rubber materials that can be cross-linked or chemically reacted to give you a long-chain polymer with what you saw before, these tremendous abilities to extend and withstand running down the road and over rocks at high speeds. That's pretty handy. And then other things, polyhexamethylene adipamate amide, which is nylon 6,6, and it's called that because it's got chunks with 6 carbon chains. It's a copolymer. And then nylon 6 itself, which again has 6 carbons in it. This is kind of a generic form for a protein. It's probably not important. We have PET. And then the other polymer that you have to memorize is polycarbonate. All right, that is going to be number 7. Okay, so keep that in mind. It's something that it's not hard to memorize. That's why I chose it. All right, but it does bring in the carbonate structures, and it does bring in phenyl rings, so it's a useful thing to talk about. And we also have polyurethanes, which you don't need to memorize. All right. Any questions about all that? Yes?
This information isn't going to be on this upcoming
This, yeah, is not going to be on the next test, all right? So that was Monday. All right, Monday's lecture was the last one. This is the next test, third midterm, okay? But hopefully some of this information was useful review today. I mean, I went over a lot of stuff that you guys may not have been as familiar with as you wanted to be. Okay, so see you on Monday, right? All right, have a great fall break, right? That's what this is? Yeah, okay.